Welcome to the Omar Alayli Podcast, your go-to podcast for exploring the diverse fields driving space exploration and technology. I'm your host, Omar Alayli, and today I'm thrilled to be joined by Professor Olga Bannova, the director of the Sasakawa International Center for Space Architecture at the University of Houston, where she leads the world's only Masters of Science degree in space architecture. Olga, it's great to have you on the podcast. Thank you for making the time.
Thank you. I'm happy to be here.
Olga, the Space Architecture Technical Committee of the American Institute of Aeronautics and Astronautics formally defines the field of space architecture as the theory and practice of designing and building inhabited environments in outer space. You've gone further and championed that space architecture should be its own integrated field rather than an offshoot of engineering or interior design. Could you unpack what it truly means for space architecture to be a distinct, highly integrated discipline? And why is integrating this view so critical for the success of future space missions?
Yeah, thank you. This integration part is very important, and architecture in general it is about integration. Integration of different aspects of built environments for people that will serve people the best, serve their purpose, what they need to do. So that's why it has to be integrated. And to understand how we can better build in space or on Earth, we need to know why we do it, where we do it, who will be working with us, what kind of disciplines need to be included, what kind of systems need to be included. So you cannot avoid being integrative. You cannot design something, it's almost impossible. I think that is completely abstract. We always have these surrounding conditions. We always have exterior and interior that we need to deal with, that we need to design for. Also, if we, for example, is analogy with urban planning and design in urban architecture, we design for the infrastructure. We're always talking about considering urban fabric. So it's always in relation to that. So in space, it's the same thing. Yes, there is vacuum, but vacuum is conditioned. If we're talking about not on other planets, but in space, then it's microgravity or zero gravity conditions. It's a condition. If we're talking about infrastructure that may not be present at the location, but then we need to design and think what needs to be there before humans arrive. So then it's much bigger than just the habitat. So to design a habitat, we need to understand what part that habitat will serve and will take within the whole mission architecture, mission planning. And of course, I understand that missions, space missions, exploration missions are planned by agencies, are planned by all sort of scientists and agencies, professionals. So we have to be at least part of it, but we have to understand why they do it. That's why it's part of educational process. That's a part of any master project almost, that students look into overall mission. Then they can focus into some part of it, but they need to see how that fits to the mission. So again, that's why it's integrative.
Cool.
And many of our graduates, they work for the industry. That's exactly their jobs. They are integrators. They integrate in different types of structures, systems within the overall architecture of a habitat or station or else. Yeah.
Okay. In your curriculum, you challenge your students to become system thinking architects. What is the concept behind becoming a system thinking architect, and how does teaching that systems level mindset disrupt the traditional aerospace engineering then space architecture workflow?
That includes, of course, system engineering, understanding the approach, understanding methodology that is used in system engineering, plus human factors. So that's why system thinking. It's part of this integrative process as well. Our students come in with different backgrounds, and they work on team projects at least one semester, and that's when they start learning how to talk to each other and benefit from each other rather than compete. Who is the boss? Who knows better? And another thing is it's always important for us as humans. It's what I believe, to step out of our comfort zone when we learn something and we're trying to do something, because then you learn faster. If you continue doing the same thing, for example, with this, even within the architecture, this and the great knowledge of architectural elements, architectural methodology. But if you don't appreciate this opportunity that you look at this engineering creativity, engineering systems, and how that can be integrated in the habitat or in the base or in surface architecture in the best possible way, then you won't learn much, right? So it's really pushing uh, yourself and students out of their comfort zone. Maybe it doesn't sound very good, but maybe it sounds some sort of mm, intrusive or whatever, or maybe it's other way around. But I think most of them at least appreciate that, and then that's how you learn. And that's why they come to the program actually. It's exactly when they want to step, they want to see a larger picture.
Okay, so what specific skills or even mindset do you work to instill in your students to have this paradigm shift?
Well, that's exactly to see the bigger picture. And for some, that is exactly what they need to see, to start with seeing this overall, again, mission planning. When you start designing one element or one specific, trying to solve some specific problem, defining the problem, that is the most important thing. It's very difficult to find this real design and research problem. I understand that, of course, if you go to NASA website and they have those technology gaps, and it's great uh, reference material for students to look at, but it's very much beyond that, because the gaps, yes, there are the gaps that we need to research and develop technology for to fill those gaps, but those gaps are because there are some problems, right? And defining these problems and defining some maybe another that are not exposed problems in design process or in designing certain elements of space mission or surface architectures, that's what they need to learn how to do that. And there are not many people who actually can define the problem. Many can work when this already, they're told, and then work very hard and very effectively to solve this problem, but define where the problem is difficult. So that's one of the things. Another thing, of course, for those who come especially from architectural background, so that's tend to be again this large picture approach, but then they need to learn how to focus and how define that even gaps or problems again. So this is two ways, and then when they meet, that is where success happens. And when they work on their team project, and then the result is good, right? So
In aerospace engineering companies and agencies, space architecture is still, uh, I get the feeling, still a little bit marginalized. What is there any what needs to be done to align engineering and the space corporate culture with this view of integration of space architecture on the onset? Does it make sense what I said?
yeah, yeah, absolutely, and you are right. And we have been talking about it within our TC technical committee. We almost always discuss this.
Hmm.
And of course, you cannot demand you come and say, well, I'm so great, I'm a space architect. Now I will design the best possible habitat or base. And then that's how you do it in space. First of all, of course, none of us on Earth have designed and built something on as a celestial body. A great success, of course, of the International Space Station and previous stations, also successful experiences. That, of course, we learned a lot from them. Again, involvement of architects, designers in those experiences, those stations, very well known. Right now, we know more about even about Galina Balashova, who contributed a lot to Mir station design, and of course, famous Lois designs for Skylab, and how he insisted on certain elements, architectural elements, to be added there. And that was added, and that was actually a successful addition to that. For the International Space Station, even though, of course, there were architects working on the projects related to that at NASA, few of them graduated from SICSA, but before even we had Master of Science in Space Architecture. So they graduated as architects, but then they worked for NASA, JSC. So there are examples, but again, it's not, they even didn't have that. We're always talking about titles. So they didn't have titles, space architects. I think at Blue Origins, a few had these titles, but at the end, it's still, they do system engineering, something approach.
Exactly.
I don't really care for titles that much as far as the position of our position and our contributions heard and discussed at least and considered seriously. Whereas us as the society's technical committee members or those who work in the field. So the only way how to make the space architecture discipline truly recognized by the field in everywhere in the world is just do it, working in it. And so now more and more of, again, our graduates and other architects are working for the field. So doing just good job and progressing with that. So that's the best advocacy for the discipline. At least now in space industry and this commercial space, when you have a degree, or like our degree, at least here in the Houston area, it is recognized. It's not something like what, scary or strange. It's something. In reality, you have to get, when you apply for a job, the first person who sees it is HR, and they have their list of requirements. And that's where we need to get. We need to get on the list that this degree is acceptable, and that happens slowly but surely. Again, on the other hand, the whole space exploration is not that old, right? So it's what's just a little bit more than 60 years. I'm talking about human space flight, of course. Yeah. So we have a few years ahead to to catch, and then the more work needs to be done there. So more different types of structures and more stations and more nations are interested in, again, exploring different avenues, commercial research in space. But the demand will be coming. So the thing is, I think it's, again, why it's important, again, and also for our program, that we will be ready for that. And we are ready for that. We are ready for that demand. And it happens. So, of course, there are many issues related to many issues on Earth. But again, if finally space becomes more sustainable, again, we're always talking about return of investment and then there are potential resources. There are many ways how it can become sustainable, all the efforts in space. Then it will be more
Opportunities.
demand opportunities and demand for space architects as well. Again, maybe in the other thing that space architecture education and in general as discipline should be focusing and offering to the industry, that involving space architects, it's not about making things more complex and more expensive. It's about making things more livable and optimized and more life centered, not only humans, but also if we're talking about plants, so it should be spaces designed for plants or whatever. So different aspects of life as well. So that's what it will be. I know, like on Earth, I don't know if you heard that, but I heard this people were saying, like if you build a house, let's say, so don't involve like now construction companies, they can do it, they have all sort of designs. Don't involve architect. They make things only over expensive and too expensive stuff because they start whatever. So I think in space it should be completely opposite, look completely opposite. We make things more, not just cheaper but more optimized,
Yeah, for
which
the
is in the
well-being.
long run, yes, there's low maintenance costs, easy for people to use, easy for them to adjust to different types of activities and so on.
Cool. Olga, your recent work on lunar colonization strategies referred to progression of class 1, class 2, and class 3 habitats. Could you define these classifications for our audience and explain the strategic importance of thinking in these evolutionary phases?
Sure. This classification was created by Mark Cohen and Chris Kennedy. So I think that's they first mentioned it. They wrote a paper together. And class one is prefabricated hard shell modules that we use in our space stations so far in orbit. So pretty much all of them except for beam, hard shell, pre-integrated. So everything is installed on Earth prior to launch to space. So you can test your systems. You can test things how they are located. So you can really secure everything for the launch. And once it's in position, connected to power or to another structure, to another module, it's ready to use. So you don't need to do anything. I'm talking about, when the crew arrives.
Plug
So,
and play.
class two is deployable structures, inflatables are included. So here we can refer to beam. Those
For
are
our audience, beam is the Bigelow
Bigelow, yeah. So
inflatable that is attached to the International
yes,
Space
so that
Station.
was a test, and it proves that it works well. But of course, with inflatable structures, it's really makes sense when you have a larger radius, a larger structure, then you can gain more. So the benefit is you can pack everything to fit your launch payload shroud, and it deployed once it's in space or on the surface of Moon or Mars, for example, on the asteroid. I don't know. And so that's obvious benefit because we can pack, we save on the size, we can launch it together with, let's say, hard shell class one portion of this habitat. But the not convenient part of that, because you cannot really put anything inside, and once it's deployed, then you have to integrate systems inside it. The good reference for that, of course, also Bigelow and now then Sierra Space inherited this technology from Bigelow, and Bigelow bought the technology from Transhab, technology from NASA before that. You need to deploy it, open it up, and then you need to arrange everything inside, not only systems, utility runs, but also separating it if you not floors, but again different segments. So it's a lot of installation. So that requires crew time. Uh, and another thing is you need to you need to integrate something hard into this inflatable structure, such as hatches and bulk heads and hatches and windows. We want windows for the crew, it's important. And again, all windows make it heavier, but also it's potential for leakage, whatever you put inside. The same actually in hard shell, the same thing. As soon as you penetrate the shell, pressure shell, so then it's potential for leakage. But anyway, that is a great thing to have. And the third class is the one that you can use in situ resources on the surface of on the planetary surface, let's say. And that, of course, ideal for long term. And it's, of course, great if you can do it. And it's similar to what early predecessors on Earth used, right? So building using our local materials, that would be the best. The problem is with that, a lot of technology needs to be tested in situ. We need to see how things will work in partial gravity conditions, let's say. Of course, there are proposals for 3D printing, and that requires heavy equipment, and it requires a lot of power, and everything requires power. So power is something first that you need to think about when you design for base or even for a habitat. And just small, doesn't matter, small or large. So power is requirement number one. Communication number two. I don't know. It's kind of everything all together. One depends on another. And then potentially thinking about evolution of habitats and uh, minimizing our logistical dependence on Earth, on Moon or Mars. Of course, moving from architecturally, from in situ, to in situ resource utilization architecture, from class one habitats that are delivered from Earth, same as class two is still delivered from Earth. So that would be ideal. I really believe that we probably have to plan to use them per use, right? So per function. So something will work better for one thing than another for another. I don't really think that we can abandon one stuff type and completely move to another without using benefits from both, especially class one and class two. Of course, and that's referring to our project that we did for Marshall's Space Flight Centers. It was them who proposed this project for a team project for students for several semesters, but it was different groups of students. So we looked at this. What would be the major driver for that evolution to happen? And what are the strategies can be used? Including, of course, all this risk management, including the increase of the number of people on this surface. Again, people who will be living there, it's not just they come to stay on the moon doing nothing, right? So it should be a reason. So that's how we always start working on any project, how I see it should be done. That first of all, you need to talk to your client, right?
True.
And think like your client at least. So what would be the major function, the major thing that you will be doing there, why you're there? And then from that, of course, you try to come up with the concept of operations for people, for the crew, who will be where, how many EVAs will be happening. Do you need even EVAs? We always want to minimize it. What kind of robotic systems will be needed? What is the sequence of deployment on the surface? And potentially, if we want to move from class 1 and 2 to class 3, so what would be needed there? So how it may happen. We looked, also last time, students worked on it. We divided it in 3 teams. Each team looked at different driver for that evolution to happen. So one was logistics. Another one was availability and capabilities of specific structures, class 1, 2, and 3. And the third one was, again, operational, so concept of operations.
Hmm.
That was quite interesting to work exercises, different strategies. The thing is, unfortunately, on Moon or Mars, there is no livable atmosphere. So we're still talking about pressurized structures. We still have to have atmosphere, good atmosphere inside our habitats, maintain it. Also, it has to be a pressurized structure and sealed structure. And after a number of years, everything loses its integrity. Everything seeps its atmosphere. So, plus in closed environments, things people are living, plants are there too. So stuff starts growing, and it will become more and more difficult to maintain it, or it may become uninhabitable at some point. So that was another um, aspect to look at, and I'm very interested in. So what happens to those structures through the whole process of then being new and livable, and then semi-livable, and then maybe completely obsolete becoming. So it's not like we will have to, well, we maybe have to bring new modules again on this to the surface, but maybe by that time that's what we need to do. So already use in situ and build something. But again, those structures also not forever, how it will be. So it will almost becoming nomadic. So you build, you live for some time, maybe 1, 2 generations, and then you move to another. Or we need to come up with a strategy how we can clean this or repair it, the structure, and live there again. But it's interesting. Um, it's an interesting problem to solve.
Yeah, actually, I know that Professor Justin Walsh, the space archaeologist,
Yes.
he would rather also preserve them as a heritage.
Probably, again, how many you preserve, and it will be then covered with these remnants of this. How you preserve it, it's another question, and what you do it with preservation. Yeah, absolutely. Well, there is, of course, a project how to preserve, and I think Apollo sites are considered as a heritage, right? Human heritage, so they need to be, protected.
Yeah. Okay, so let's zoom in a little bit onto one of your recent projects, which is the hybrid module design, which proposes 4 distinct module types for a lunar colony. Could you walk us through how these different components, like the vertical habitat, the horizontal labs, and the connecting nodes, interact with the site and themselves and grow over time to form potentially resilient, adaptable settlement?
That is to benefit from different types of structures, different types of modules, and then again use them when they need. Again, vertical structures, of course, vertical habitats is it's easier to land, maybe, especially with vertical type of stacking on the land, but it's difficult to bring it to the surface. That's actually the one of the biggest issues, how you not only land but also how you bring your modules to the surface and then transport it. It's difficult to solve. Plus, again, with all that dust on the moon, that once it's disturbed, right? So this kind of stays there for a while, and we want to avoid this contamination as much as possible. So that's important. So using different types of, again, vertical versus horizontal oriented. Again, it's just what is the purpose of the structure and how you can use floors in the vertical, but then you create vertical circulation, not only horizontal, but it both circulations. On the other hand, you separate the functions, maybe better and easier. With horizontal modules, they may serve better for labs and where you need to put people and they function in one floor and they will communicate better with this case. And of course, considering inflatable connecting corridors, that's another thing. But remember that even though it says it's soft connecting, but it's once they deployed and pressurized, it's not soft, it's rigid. So aligning modules on the surface, which is also uneven, that's another issue that we need to design for that. And that a potential problem for future expansion of the base. More modules you connect, more alignment will be happening with potentially different differential settlement that may happen. That may also disturb the functionality between the modules. Again, thinking about contingencies, what happens if something, for example, one module is hit by micrometeoroid and depressurized, started losing atmosphere. So how people and where people evacuate and how that will be happening. It should be possible to disconnect it, close the hatch. So that's again interfaces between the connecting corridors, tunnels should be secure. Again, yeah, something happens, so it should be possible for people to quickly to escape to safety. So that's is the major idea. And again, combination of different geometries allows more flexibility with how you connect stuff, how you connect modules. We did this study many years ago about different geometries, for example, cruciform versus triangular shapes, configurations on the surface, and evaluated pluses and minuses of that. Again, how many hatches you will have to connect more modules, where it could happen. So, and again, of course, considering safety. So safety is always our priority. So how you provide safety for the crew. So that's the major thoughts behind those different configurations on the surface. Again, those are mostly combinations of class 1 and class 2 to again benefit from both. With class 3, still possible because you can do a kind of hybrid between those class 1, 2, and 3 when you build in situ just a protective layer using local resources, regoliths, and put your habitat inside of that protective layer. So that is a combination of again benefits of both structures, but not pressurizing this type 3 or class 3 yet.
Okay, let's shift gear now to radiation. In a 2024 paper, you argue that space radiation is not a showstopper for human exploration. Could you explain your argument that radiation should be viewed not as an insurmountable medical barrier, but as a complex architectural and systems engineering problem that can be solved with intelligent design?
Yes, I'm happy talking about that. Yes, because technically we can look at any environmental issue on Earth and, of course, in space as a showstopper. There are many places on Earth where people are and or explored and living now that potentially was completely before people got there and figured out how to deal with it were completely inhabitable. So radiation is a big issue, but it can be dealt with if we combine different types of radiation protection and just again benefits from different materials, different strategies, and see what you can integrate where and what you can use where. Of course, most radiation protection means and most radiation protection strategies right now are against solar flare events or heavy particles events, and those don't happen all the time. So that allows us to design, for example, for them or deployable shelters. That's what we proposed back then when we worked on minimal functionality habitable element before. And we proposed to have a deployable structure within the habitat that will be filled with water, and you need to bring water with you anyway. So that's something that can help you to sit there and wait till the storm is over. The issue with that, of course, the storm can last for quite few hours. And of course, you need to provide for the crew inside the habitat for that, inside the shelter for that. Also, they should be able to communicate, right? They should be able to see what's going on outside, to get information. So that needs to be also provided. So that's something to consider. And also talking about in situ resource utilization and building these structures outside of the habitat, creating artificial caves, if you will. So that will help. We still have to deal with cosmic rays, galactic rays, and that radiation is always there. It's only blown away by solar particle events, but then you deal with other stuff. So there is never radiation-free environment. So it's always one or another, and then also on the surface or else, you need to deal with secondary radiation as well. So that's again on the surface. On one hand, you are protected because you have the planet or the moon underneath you, but then you have secondary radiation that you need to consider to protect humans from. So using new materials and using integrated those materials in the habitat shell structure, that's another option. And there are some research proposals to use mycelium inside this structure, wall structure of the habitat. Again, needs to be, I guess, looked at from systematic point of view, because what it requires, it's argued that once the mycelium grows there, then it dies and it stays there and it becomes just a part of structure. Everything requires tests, and everything requires the better testing in situ. That would be the best, of course, but at least in some conditions close to the surface conditions where we will be building. Yeah, so that's what I was talking about. Perhaps paying more attention to areas where humans will provide, humans will be spending most of their times versus less time. And again, luckily with solar particle events, you have some time, right? So you know it's going to hit the moon, for example, and it's like, okay, 20 minutes or something. And on Mars, it's longer, a longer period. So at least you have time to run to the shelter, deploy the shelter. Uh, but still, you need to provide for that. And again, galactic cosmic rays need to deal with it. Um, yeah, there are also research proposals and I think tests to deal with that issue using medicine, certain medication that helps to withstand that effect of radiation. Again, protecting the most important body parts, body organs. So that's another. So again, it's a combination of many, many things. And I guess it just needs to be included in the routine, how the crew will be dealing and what they will be doing. So, and perhaps people, if they stay long enough, so some people will be, I guess, we will be uh,
Adaptable.
adapted or, yes, or modified according to the environment. So if we're talking about, somebody will be born on Mars, let's say, so it will be different species, I guess. Yeah.
Yeah, true. And yeah, people are sometimes considering gene therapy for adjusting the human body or the microbiome on the skin to
Mhm.
act as a sunscreen or radiation resistant. Yeah, there's a lot of science and research being done here. Olga, when talking about lunar habitat concepts, we cannot not talk about lava tubes. So lunar lava tubes are often hailed as ideal location for future habitats due to their natural radiation shielding. Your research has explored this avenue. From an architectural and robotics standpoint, what are the primary challenges we must solve to first survey and then actually build inside one of those massive subterranean caverns?
Yeah, so it's very tempting to say that wow, we have already holes ready, so we just go there. Well, first of all, we don't know yet what to expect from them, and it is expected that they are much larger on the moon and Mars than they are on Earth, just because of less gravity there. And again, it's not like it's a human ready environment. So we need to modify that lava tube that if we find it, there is a famous picture on the moon that looks like it's a lava tube's hole. Again, radiation shielding, yes, partially, but it still will be secondary radiation because it still happens, hits there. But of course, it's a better, more stable condition from temperature fluctuations point of view. So it's less fluctuations between cold and hot temperature like it is on the moon or Mars. And so there are many benefits would be to use it to build something. Still, again, to get there, we will need to create a good, convenient, stable, and safe way to get in and out. Building inside, perhaps it still will start with just again same type 1 and or class 1 and class 2 habitats brought there. How you will bring there, again, remember they're huge and very deep. So how that will be happening? We modify the entrance to. It's interesting enough. I tried to find it, but maybe I didn't dig enough. I don't see many examples on Earth from indigenous people on Earth from living in lava tubes. Yeah, caves. They lived in caves. Lava tubes, I didn't find any examples yet. Maybe there are. Again, I'm not archaeologist. Maybe I need to talk to.
Yeah.
Well, uh, but
I think in Turkey there is cities, underground cities, but I think those were dug by humans. They're not like existing lava tubes that are being
yeah, yeah.
reutilized.
So those lava tubes that found on Earth, I never saw that they were like our predecessors used for habitation for whatever reasons. Maybe because they had enough caves where they can do it more conveniently, but interesting. Yeah, and also once we are there, and again, I'm not talking about those proposals to pressurize the whole cave because, again, that is completely unpredictable because we don't know the size and that how much even atmosphere we need to bring and pressure. It's tremendous pressure and yeah. So, anyways, there are so many questions but once we bring there, let's say we brought there our habitats and we deployed them there successfully, we connected and we created roads to come in and out. We still need to think about communication and power and all of that, right? People also like to see outside sometimes, so need to think how we provide some, again, light coming in, or at least to have some ways how this imagery will be brought to the habitats inside for people to feel less isolated. But then we change also the environment outside. So once we create all that commotion and these activities, especially if it's a large scale habitable system or settlement. So what happens to that structure? we change that environment. So would it be still safe to stay there if something may collapse? Again, I'm not a geologist, so that's what would be nice to discuss and work with planetary geologists. And especially, of course, we need to do at least local robotic missions first to figure out how deep those caves are, how big they are. And yes, there are so many unknowns. But that's something that really interests me again. So, how we can predict, or how we can, or what we can predict rather, and how we can prepare for those potential changes in the environment around us. We, as people, we always refer to, first of all, to our lifespan. It's just what we are. But if we do something, again, we need to think again, plans ahead, right? Against the same thing. So what happens to those structures? And also really thinking in long run, what we will be doing to that environment also. It's not only us, right? It's also what is outside us. Talking about safety, if something happens and then that entrance to lava tube will be blocked or whatever, something happens, so how people can escape. So we're always talking about two egress points from any habitable volume. Same thing should be again for this for the lava tube as well. Again, we're talking about they're big. Well, again,
Okay.
aliens may come and block us.
Okay, let's now talk Earth analogs. Analog missions have been conducted on Earth for decades, and testing lunar designs on Earth analogs has been central to your work as well. From your perspective, how have those test beds evolved since your early Arctic studies? And what are the most significant lessons we've learned from these Earth based simulations?
I can say from a space architecture point of view, not much, unfortunately. A lot was learned about operational, so a lot of psychological studies about human behavior and operations in isolated and closed environment. So those are all good and very, very valuable. But unfortunately, architecture is even design in general, so that's not part of it. Even though, of course, we know Hera, and it is the module, shell module with simulation of inflatable, which is not true inflatable, it's just the volume. So it looks like it, but it's not what it would be. So inside you will find this regular furniture and regular types of how these things are arranged, except for maybe sleeping quarters. Sleeping quarters are the top. They probably will be very much like in real inflatable uh, modules like that would be. But yeah, so from architectural point of view, that's how architecture, internal architecture, external architecture is affecting human operations, so human dynamics, even crew dynamics. It's not much, even though many of these studies focused on, again, these particular things, group dynamics, analyzing this behaviors, health, analyzing this. But just focusing on this, on the team, on the crew, not on this exterior, what is around them, let's say. Not in the reference to the exterior environment only from this point of view that it's isolated and it's closed and they cannot leave, for example, for a year or for 4 months or for some time. So that's unfortunate. So on one hand, yes, it's very, very useful, and many very useful information was gained from human behavior and crew behavior in relation, in connection with, or in interacting with the environment. Not, and again, yeah, that's unfortunate.
Yeah, but it's very true. Like it looks like we're those Earth analogs overlook the equally important validation of hardware, system integration, and even the architectural layouts themselves for the for crew circulation
Mhm.
and other stuff. How do we ensure, if we can, analogs that test the built environment as rigorously as they test the crew inside it?
You just need to do it. So need to give more flexibility to the design and more flexibility to the crew what they can do it. They usually crews in these studies they're given what is there. They cannot even change it even if they want it. So it is what it is. It's not even part of it. I think if we start designing with that set of mind, that giving them some opportunity, even without telling them do it purposely, just uh, emphasizing that their crew quarters or their command control maybe most likely will be what is, but some certain areas where there's for example galley or something that it is it's flexible and they're free to change something, and maybe giving them some means. Let's say again 3D printing. 3D printing will be inside the habitat, will be part of any mission on Moon or Mars. That's for sure. You have to have it, even just to reprint some tools or something like that. So doing that and giving them more freedom, that will be very useful. And I think it will be something that can be tested. So far, yes, because the part of it that there's big analog missions, not designing for them or building for them, these mock-ups. To build them is very expensive and they require a lot of space. So at the end, of course, everyone is trying to do it, first of all, cheaper. Secondly, you do it and you can keep using the same thing for years, like what happened Mars 500, for example. Now it's been used, the same facility used for several serious studies. It is exactly the same. They changed this EVA area from Mars to Moon, but it's the same. The concept of operations is different. The time delay that included in again operational scenario is different. But the design is absolutely the same. Again, it's expensive to change it. It's difficult to change it, as everything is built out of plywood. Again, the major changes. With Chepia, that was 3D printed inside this Johnson Space Center, right inside. So could be tested most things maybe than and again whatever design was. So it's again focused design and everything almost was the layout, let's say, secondary to this 1 year study of the crew inside. And again, it was mostly group dynamics, and it's all related to the concept of operations and simulation of Mars missions with delay and stuff like that. So the structure is different. Interior of that and the how say spaces are organized probably will be different on the Mars. But that's again, the focus is not on the specific layouts or how space is organized. It's focus on the crew without this interactivity part. That just I think will be very useful.
Okay. Um, let's shift gears now and go back up to space and talk about the artificial gravity science and excursion vehicle project you worked on, which was sponsored by the Bigelow Aerospace. That was a fascinating project. Can you tell us more about this project? And then could you share some unique challenges of designing a commercial vehicle that incorporates artificial gravity?
Correction. It was designed by fifth year students, architecture students, and it was right before my time at SICSA. So I didn't work on that project. I worked on
Okay.
this next year following project, and it was commercial space development plan. That part of it was to design a construction facility in orbit that will be servicing that vehicle, artificial gravity vehicle. But I know the project very well, and I love the project. And we have this model on our wall over here, and it's again.
And you wrote an article about it, right?
Yes. Uh, and again, that's a wonderful story, and it's a wonderful project, and what students did. And it was 1999 2000 academic year. Uh, they used already 3D Studio Max, and it's a very early version of it. So that's quite impressive. So I really a big fan of it. Big fan.
Yeah.
So the idea was to have an excursion vehicle for 75 passengers, 25 crew, to go rendezvous around the moon and return to Earth. And then this way, crew exchange and passenger exchange will be happening, obviously. Then, of course, Bob Bigelow wanted artificial gravity as part of it. And for that, it was decided to use not truss system, but cable systems. And those cables would be built or manufactured in space. And that was actually part of also that next year project as commercial space development plan in orbit. So those cables would be developed in orbit and out of fiber and fiberglass. And they would be very strong, of course, because there is no air and vacuum. You can really produce a stronger material. So you know that. So that was the idea, and everything would be assembled in low Earth orbit, and then with inflatable modules used for crew and passenger habitation, and the core with chemical propulsion system. And once it's an orbit assembled, it was moving towards the moon. So those habitats on both sides will be expanded from the core, and the core starts rotating, and that will simulate gravity. So, of course, big part of it is dealing, when you talk about people inside, cross-coupled acceleration affecting humans, and also Coriolis effects, all of that. And designing for that, it was a challenge, of course, for students. So the idea was that it will be, again, once it's rotating to the moon, then they enjoy this random weather and they're coming back, and it's again put back together, then it's zero G or microgravity conditions, and then again the exchange will be happening between the crew and well, this thing is, again, artificial gravity as an interesting design challenge from both points of view. Definitely, it's a big issue, big engineering problem, how you provide for that. And secondly, of course, for humans, how you design for that environment when you heavy on one side and you lighter on the other side. What happens between when you switch from zero G to partial G conditions or 1G, whatever, rotating environment. Again, it's not exactly gravity, right? It's the forces that push you again. So we don't know how fast people adapt to it. I really believe that people adapt, and then after few confusions when you cannot touch your nose or whatever, we adapt, and then should be easy to switch back and forth when you turn one way or another. Again, those rotating environments and people in rotating environments, we only tested on Earth. So on Earth, we have still gravity. So it's not exactly the same when it will be just centripetal forces. Uh, Again, what's probably needed is, again, same thing. Need to build something maybe smaller and test in orbit first and see how humans will be adapting or not. But it's not only humans. We need to think about fluid dynamics. So how systems will be working, and not only water, but also air. I don't know, sewage, right? How everything will be working there, how all systems will be working. So perhaps everything has to be designed specifically for rotating environment. So maybe then it will be dual systems for everything, for air and water, and well, anything fluids. Air is also fluids anyway. So dual systems for zero G conditions and for rotating conditions, artificial gravity conditions. Do we need it? Artificial gravity? Probably yes, when we go farther, when it's a long trip to Mars or beyond, if we use different propulsion system. Yes, because we talked about radiation issue, but lack of gravity is also very dangerous for humans. Again, is fluids are shifted up and losing muscles,
Bone density,
losing
muscle,
bones. Yeah, so and even
muscle
with
atrophy.
muscles, at least we can do exercising, but exercising is not that efficient for bone strength. So you're losing calcium and everything. So perhaps it will be required for long duration flights to have artificial gravity. Again, the whole ship will be rotating. We're talking about O'Neill's rings and stuff like that. Again, if that many people will be going, do we like depends how many people will be going, what you're designing for. Maybe just having a centrifuge will be a good additional element for as a countermeasure.
Yeah, very interesting questions.
Cool. Yeah.
Okay, so let's move on to inflatable structures. You talked about them a little bit earlier in our conversation. So inflatable structures offer incredible advantages, like you said, in packaging efficiency, let's say. But your work, it makes it clear that it's not a magic bullet, right? What are the most critical engineering challenges that must be solved to make an inflatable habitat as safe and reliable as a traditional rigid module?
The major thing again is the penetrations and how to design it so minimize the potential for leakage. Uh, that's that's a challenge, of course. Again, having lighter systems for all these penetrations for windows, for example. What kind of materials? Again, not obviously we're not using glass, right? Yeah, so that is the challenge. All these beautiful pictures with huge windows is great, but how feasible is that? A larger window will be nice to have, of course, probably even on the moon. See Earth, especially if you see Earth. So yeah, that's a big issue. Another thing, of course, how we can integrate maybe radiation protection layer within the structure of inflatable. Again, inflatable is, of course, this pressure bladder is the main thing. But then we have the whole stack of insulation material. For thermal insulation, again, micrometeoroid protection, and all of that, right? So most efficient materials will be the best because we still want to minimize this pie. Yeah, so it's about packaging. So because we want to package is the most efficient way. There are different external layers types, and again, minimizing this, how brittle they are, using different types that may be inflated once and then they can be rigidized. And there are materials like that. So ILC Dover has been working on those different types of inflatables for years. So these are the challenges. Again, you designed for purpose. They Good thing about inflatable structures, not only that, of course, they provide more volume for you, but also once we inflate them, it's not like we will be deflating them and moving somewhere. Once we inflate, it stays. And once it's inflated, it becomes pretty rigid because the pressure pushes it. There's a lifespan of those structures. That is something to investigate, of course, to see how long they can last before they start losing their integrity.
Yeah, start
That's
leaking and stuff.
something
Yeah.
to consider. We want to minimize any loads on the exterior loads. That's why we don't want to throw regolith on top of it, right? So we want to have it protected. But inside as well, because we need to have secondary structure to put things around, to hang things. We don't want to hang anything off the bladder, pressure bladder. So these kind of issues. But I think mostly it's, of course, related to material science. That is the challenge. And of course, figuring out the most safe way to integrate these hard elements as pressure hatches for doors, other interfaces, and windows. Yeah, that will be something.
Okay, so let's talk about now the unit inflatable tower project, which by like it's designed to stand over 30 meters tall once inflated. It represents a conceptual leap from inflatable habitats to inflatable architectures. Could you give us an overview about the unit and describe its deployment sequence for our listeners?
Yeah, that was students were working on it. It's a student project, and yeah, that was pretty cool. We consulted with ILC Dover specialist John Lin. That the idea was we wanted to have it as light as possible and easily to deploy. So that's the idea was again to incrementally inflate it, level by level. We had this again in the middle, this counterweight that will help to stabilize the structure. Still, the problem would be, and that's what we didn't address enough, and we needed to collaborate maybe more with mechanical engineers on that. Well, what kind of pump you have, where the air, so that's part of it's always kind of left behind, but it's important to have, right? So the idea was to, again, once it's deployed, so it can house different types of equipment, including the solar panels, but it's also communication device and all of that. We propose to build a smaller scaled structure here at the University of Houston. Anyway, that would be nice to test. And that would definitely require, again, to figure out so how you pump. What is interesting is because it's deployed section by section, so we need to have valves. So once it's deployed, it needs to stay. It's not like that air will be. So it's not exactly the same way how you inflate, for example, I don't know, balloons, right? So like several balloons together. So, or like I have my Saturn inflatable model behind me. But so that's important that once first base, let's say, is deployed, so it stays. So it's becomes rigid enough, and then you deploy second one, and you deploy second. So it's you are not starting from the top; you start from the bottom, and then it helps to stabilize the structure because again, it can be uneven terrain, it can be in an angle, and that's what is demonstrated in that video if you saw it. Uh, so that's something that we really paid attention because with inflatable structures, one of the major issues, another for engineers, by the way, your previous question is to have stable inflation process and stability of the structure itself on the surface during the process, but also during the process inside the structure as well. They did have this issue with beam inflation, so it didn't deploy right away, right? So they had to do it incrementally. So that's another thing that we really paid attention in that project. So it would be inflated once and then another section and another section. So that was something. But yes, it would be nice to pay more attention and put, again, more time to work on the mechanical systems for that structure. That would be cool. And again, use what kind of material can be used for this inflatable tower. That's another for the inflatable itself. Of course, you don't need to worry about thermal protection. It's not a habitat. Micrometeoroid protection still will be needed. And again, for that structure, it can be deflated and it can be moved to another location. So that's another thing. But again, this sequence and this sequence, what is again once walls closing and then you inflate another one and inflate another one. That's was
Okay.
interesting.
So, Olga, you began your career as a professional architect in Moscow before coming to the US, and now you collaborate with partners globally. From your unique vantage point, do you observe any distinct philosophical or technical differences in the approach to space architecture between the Western Bloc space agencies and institutions like US, Canada, Europe, Japan, and the Eastern Bloc space agencies and institutions like the Russian and the Chinese? If yes, what are they?
Unfortunately, I cannot tell you much about Chinese approach. All I know, like probably as much as you know, just from the media. So what is posted, I am really interested, of course, in that moon palace, and because again, it's a pressurized structure, and that is very interesting analog to
Yeah,
look into what they do
with a
and
closed
how they
loop
do.
life support system.
Yes, yes, yes. So that is something. By the way, Johnson Space Center, sorry to detour a
No,
little
no,
bit.
please.
At Johnson Space Center, there is a wonderful thing. It's called Hestia, this module. And this is the chamber that it can be pressurized. It was built for Apollo program. So it's built long time ago, changed names many times. But that's particular module, particular chamber can be used kind of to test life support systems, and they did. And also they did concept of operations for pre-breathing and for EVA suits and stuff like that. So that's really cool thing. But again, back to your other question about the differences. So even though Galina Balashova was one of these first probably space architects, it wasn't that much on space architecture done in Russia or Soviet Union, let's say. Although one of the, or maybe then one of the first space architects, not talking about Tsiolkovsky, of course, but a little bit later, it was a student, architectural student in 1927. Diploma was about space architecture, Kruchikov, and he proposed cities in this upper atmosphere, stratosphere, and living. His idea was to leave Earth just only for leisure, and all people will be living and working. All the facilities, factories, everything will be in space or it's in upper atmosphere, and there will be cities there, and people will visit Earth only for fun and relaxation. And that was pretty cool, especially when you think about it in relation to space era when it started 30 years later. And so this diploma was quite interesting. But again, not much was there in the Soviet Union. When I asked people at Energia years after about Galina Balashova, they didn't know about her. And
Yeah,
they
they
knew
were.
her husband, who was engineer. But
Yeah, she never got the credit that she deserves for what she like
no,
was a
no, no.
man's
Only
world. back
I'm
then.
happy that at least it happened in while she's alive. But that was something interesting because when she was already popular and the book already was published about her, I think, and I asked about her at Energy, and they didn't know, but they knew her husband. So it's probably why she was working there as well. And she started as an architect. She was doing just facilities. And then they needed somebody who would provide renderings for this. And that's how she got involved. So doing just renderings. But then she worked on this color palette for Mir, so doing more work. So I think again, my experience with people from this Russia and those who actually they all came from Soviet Union times anyway, and space industry. So it's very, very much oriented towards engineering. So it's all about engineering. It's cool that those engineers, some of the engineers who, for example, flew to salute stations, so they were also designers. So they came back and they could provide and work on the design issues as well. But uh, it's not about so space architectures was completely unknown anymore back then. Now is more known, and that was happening. Probably started happening in maybe in 1990s. So this again in Moscow Architectural Institute. So there were people who were interested in that and worked on these projects related. So Olga Zakharova worked on projects related to extreme environment and space architecture. And then just before COVID, no, right after COVID. Anyway, so there are also just a new generation, I would say, that's um, teachers and professors at Moscow Architectural Institute are also, they try to do it. So I don't know what's happening right now, tell you the truth. So I haven't been to Russia since 2022.
Okay, so let's shift gear now to extended reality and
Mhm.
your work with that. Your work has been at the forefront of using extended reality or XR for design validation. You've stated that the old way of using physical mockups is slow and expensive, and that innovation has stalled for a few decades now. Why does this shift from static computer models to immersive human in the loop testing represent such a fundamental paradigm shift for the entire field of space architecture?
You named it because, again, building this hard modules and mockups, we talked about it before, it takes a lot of time. And once you finished, maybe you need to change something, but it's very difficult to change the design. So then design left completely aside. So it's just a background or decoration of whatever humans will be doing there. Here we can do much more. So interactivity is very important part again. So not just looking around what is happening with VR set, but really experiencing the environment, dealing with it. And again, so of course, thanks to my students who did that, they were students at that time, so now they're researchers for that. So they're really big pushers for this project. And we started with how it all started. That we worked on a project for Boeing for lunar surface, very small habitat that would fit in a small lander, and that the part of it we did several studies for this lunar surface architectures and again operations, logistics operations. So crew of four, they would be the major task for them will be within 2 weeks on the surface. They need to offload logistics module that logistics not modules but logistics payloads from cargo lander. For that, they would have a small habitat, but the habitat was so small, super small, So we had to figure out how we can reconfigure it for each function. Sleeping, eating, hygiene, exercising, that was the names. No signs, nothing. They will be doing, overseeing all this offloading and packing stuff in a cargo airlock, next to, well, attached to the habitat. Cargo airlock that we used another study that we did also for Boeing, this deployable airlock, inflatable. That's what we propose, that it will be separate from crew airlock. When we designed this reconfigurable environment, important part is, again, in computer, everything is very easy, right? Here is one configuration with another. But as soon as you put people inside, how they will be doing, I don't know what is happening in transitions. So for that, we need to have, we cannot build this stuff. It will take forever and it will be wear in any way. So we did it virtual. Of course, we did 3D modeling. Of course, it was part of the study. But then we need to bring people and see how we will reconfigure it from one part to another, from one configuration to another. And that's when we started working on that methodology. Now we've bringing it further and really evaluating human performance within the environment. So you can give them different tasks, and not only inside the habitat, can be outside as well. And of course, we can ask the subject when I have students usually. So, and it's part of our now learning process as well for students to evaluate their designs. They have to do it, but also really recording this, just basic vital input from their heartbeat. I want to say precipitation, but perspiration and things like that. So, yeah, and so then we can look and see how easy or how hard that to perform that task was, in addition to individual surveys that they will do it anyway. So we really want to combine subjective input, because it's but also with objective data as well that we collect. So that's how it was evolved, and it keeps evolving. The technology changes all the time. What is available now, for example, the whole motion capturing is now it's possible and becomes actually cheaper at some point. So hardware and software is changing, so need to adapt all the time. Again, designing very low fidelity elements that can be combined with virtual elements. So it can be something very simple, like that chair that I'm sitting on, but in reality, it will represent something else. A chair on a rover, for example, right? So it can be modified a little, so because we can do adjustments, and then evaluate it, how it will behave and how you will behave, how you will interact with it. So that's becomes more and more interactive architecture. So that's what it is for, and expanding on it. So one of our researchers, Paolo, he is developing his EVA suit mock-up. Again, we don't need to pressurize it or anything. We just need to restrict the motion, and so to recreate the feeling maybe, and this evaluate this again, how
Very
easy
interesting.
this task may be performed, what needs to be done, and how you can adjust the design so it will be easier for person to do it. So that's something, again, that's what Boeing was very, very interested. So we started with designing surface elements and surface strategies, working on that, and what type of automation will be needed and all of that stuff, combining with rovers. But then they said, like, oh no, Dex, switch, develop this methodology. That is more more interesting and more feasible for them. So again, I don't think, well, probably Many are looking into this, but I think to me, more people are addressing or working on these problems is better. It's of course there is some competition, but in reality, the outcome is only we can gain more and we can learn more. So that's
So let me ask you, in your opinion, like further down the line, who are the end users or who benefit from this technology? Is it only students, master thesis graduates, or the commercial sector? And what radical shifts occur when you let the users manipulate the habitat in virtual reality or in extended reality?
well, students obviously. Again, we can use it, and we do use it when we work on grants and research here. Uh, and the industry too. So because if we do some work for the industry, again talking about Boeing, so it's beneficial for them who we collaborate. So it's more about it's more about learning how we can do a better job designing for humans, for people in difficult conditions, space, but maybe it's also very applicable to Earth too. We don't think about Earth as again some extreme environment. There are extreme environments on Earth too. But the thing is, maybe designing here on Earth using the same methodology will be also beneficial. So I think it can be used in many ways and in many industries as well. So talking about space architecture, but it's also naval architecture, and we're talking about again airplanes
Yeah,
and
and if you can
yeah,
3D scan environments and then upload them into the 3D environment, then
yeah.
yeah, true. Okay, now let's move on to the horticulture and bioregenerative systems. Your research proposes two distinct greenhouse concepts. I love that, a habitable one designed for psychological well-being, and an industrial one designed for maximum fruit production. What
Mhm.
is the distinction? So okay, no. Why is this distinction so critical, and why can't a single design optimally serve both the human need for a garden and the mission need for a factory like production farm, so to speak?
Because in one case you're designing it for humans mostly, and second you design it for plants. And humans and plants, especially in enclosed, completely sealed environment, yeah, they can coexist, but they thrive in different conditions. And again, we can really capitalize on those benefits that plants can tolerate lower pressure, but it's we need to maybe provide for them higher humidity conditions than for humans. If you have plants, just one plant or few plants inside a habitat, it's fine. So you can really take care of it, or it can be semi-enclosed or periodically enclosed. So you're not sharing the same environment all the time. In production, it's all about production. So it's about plants. It's not about you. It's about you as when you just go there to collect, for example, be maybe sometime with the plants. So again, just designing for purpose and designing for function. That's why it's different. Can benefit from using this. One of the proposals I don't know if you read it, and it was my graduate student working on that, and I thought it would be very interesting to use this greenhouse in the large. That's another thing. If you want to have significant production level from this greenhouse, it has to be very big, even for four people, even for small crew. So it's large structure. Again, if we can have it the pressure lower and this different type of atmosphere conditions, so perhaps we can use that environment for pre-breathing before EVAs. So that was a step. normal pressure conditions inside the habitat, and then humans can go and while they're doing this few hours of pre-breathing before going on EVA, they can enjoy greenhouse environment and maybe do something, just being in a nice environment rather than just sitting in an airlock. So that was the idea of this.
Were you referring to the Martian greenhouse?
Yeah,
Yeah, cool.
yeah, Martian greenhouse. But again, it can be the same thing on the moon as well. So yeah,
Okay,
but
so
that was the project was for Mars. Yes.
yeah, I remember that. Okay, so your work outlines a complete pipeline from crop selection to advanced food processing and even 3D printing food, like you mentioned. In your expert opinion, what is the single best technological or logistical hurdle we need to overcome? Um, Sorry, what is the biggest technological or logistical hurdle we need to overcome to make a truly self-sufficient food system a reality on the moon or on Mars?
The big issue, of course, dealing with waste for from plants and the biomass. So what you do, and of course we can get all the moisture out and get the water out and the process, but still stuff will be left. Some can be used for the compost. Again, the whole process, technological, how you use it for compost and what will be left. So that cycle is very important. And that also takes quite some volume and space and power. So that's the thing. Unfortunately, we need to add something to the process in order to have it all utilized. So that is the technological issue. There are proposals to use worms. There are proposals to use aquaponics with fish, and then this like it's used on Earth. So just that's something that needs to be done, and that would be, of course, very nice and beneficial if we can use aquaponics and using with fish and plants. And everything, and so not using yet much of
Fungi.
soil. And ideally, of course, if we're talking about regolith on Moon and Mars, yeah, we cannot use it as soil, but maybe we can use it as some media with just for plants in aquaponics, for example, or something.
Okay, so closing the loop in life support systems means reusing or recycling air, water, waste, and nutrients. How does that circular approach dedicate the spatial layout of habitats? How does this influence us as architects to think about our space architects to?
It's you need to provide for it. So closed loop systems require, of course, its mass and volume and power. So you need to think about where you put it and how you can integrate it in the system. If you have a greenhouse, so how that is part of it. Of course, there are proposals of using biological systems in this closed loop. But again, that becomes a very complex problem and complex issue. Will be wonderful if it can be used, and maybe it will be someday. But that's another issue that needs to be solved, and this is engineering issue. Again, remember, we don't know 100% how all this fluid dynamics again will work in partial gravity conditions, assuming that it will be similar to 1G, but maybe not. So what needs to be changed? What needs to be designed differently? And then we're talking about closed loop systems, and then we're talking about biological regenerative systems included in life support systems, and it's even more complex.
Also more complex on the habitat structure itself, like because the more isolated the small modular units that are connected, the harder the a closed loop system could operate. It requires more of an open space or shared space.
So there are different approaches, and it's like the same on the ISS, for example, on the stations in general. So one approach is to have life support system in each module where humans are. Another one, and that was approach on Mir station. I think so that the life support system in one module, and then you run these utility runs to other modules. So everything is in one. So there are benefits in both. Obviously, redundancy and safety is high when each module has life support system. But then, of course, you lose this space in each module, or not lose, but you have to dedicate that quite some space and volume, power in each module for that. So it's also something that to evaluate and optimize, and maybe places where humans are not for long period of time, you don't have to provide. Maybe you can do this, just run utilities into connect into these modules and provide air circulation, and that's all you need, air and power in those modules. Let's say it's a lab, people just come and check environment, check their equipment, and leave. So it has to be pressurized, but doesn't have to have all this closed loop system there. And if you lose it, so it's okay. It won't jeopardize the whole mission. So that's something, again, like in many cases, it makes sense to have a compromise between those two, and or combination of those two, and finding the good balance where you use what.
Olga, looking forward, your work points towards integrating AI and smart materials to create responsive habitats. How would you describe a responsive habitat in this context, and what is what it?
Well, yeah, responsive or smart habitats, right? Uh, it's always question how smart you want to have your habitat, but you definitely don't want, and none of the crew will love to have their habitat outsmarting them. So they have to be able to have a red button that you turn it off. Remember 2001, right? That is it.
Yeah, yeah.
That's
How?
it. You don't want that to happen.
Yeah.
It's very important, of course, to have the smart systems included. Again, considered even that a habitat would recognize the crew when they arrive and adjust the environment to their preferred conditions, temperature, humidity, stuff like that. Another thing, again, talking about light, so lighting. So then it can be included, and then it can be adjusted. With crew health related issues, on one hand, it would be good if something is the crew health is monitored, and if there are signs of depression or something, any disturbance is recorded and alarms somehow, not to the mission control, but maybe to the crew. On the other hand, none of us would love to have that feeling when you are watched like a big brother, right? So you don't want to get this
We
feeling
will
again.
still
So that,
value our privacy in space.
yes, yes. So again, with countermeasures, any with the crew, it's less intrusiveness is always better. So that's why, of course, it's nice to have sensors and everything, but you don't want to cover your crew with sensors that you will be monitoring everything 100%. So it's not convenient, and it's irritating, and it won't get you a good outcome anyway. So on the other hand, maybe it will be okay to have this option that, for example, you can monitor yourself when you are sleeping, and you get this private information or data at the end and saying that how you slept, and maybe it will give you something to deal with, and hopefully the crew is responsible enough to deal with that, or at least to talk with crewmates if something is not right. In polar, when I talk to people who do this overwinter operations, and it's a small crew, let's say 4 people, 4 men, and periodically somebody would feel irritated, bad, and that person that would go to his room and stay there, and the rest of them know that he's dealing with something, then nobody bugs him, and eventually he comes out and everything is okay. So the thing is, they know what to expect, and they experienced, and then they know at when something happens, when suddenly everyone, you feel like everyone is doing something purposely to annoy you. So they are trained enough to know that it's not them, it's you. So they deal with it. Again, can we rely 100% on that? Maybe not. Maybe in that point would be good to have some AI intervention.
A mediator.
Yeah, it's a big question. Whereas, again, you know, we're all different. We come from different cultures, from different backgrounds, and what is okay for one is not okay for another. So there is no universal prescription. There is no universal best design habitat for everyone. And that's why we need to design in the way how to allow them to change the environment to their liking, or adopt the environment to their needs to avoid the stress. So I don't think people were really living in those analog facilities, like, let's say, Mars 500 on Mars, it will be okay for one. Yeah.
Finally, if you could secure unlimited funding for one high risk, high reward research project, what would it be and why?
I still would build a full-scale analog facility, but that's with including this aspect that we were just talking about. Just allow people to adjust, interact, and with the environment, and see what is happening there. So to include as much as possible of their input, and being able to collect that input to learn from it. And another thing, I would like to have a big vacuum chamber.
Nice.
And put, regolith over there, and put a habitat there, and then it just really
So
test.
to validate design ideas and stuff like that.
Yeah. So
And test
to
them.
test.
Cool. So before we wrap up, is there anything else you'd like to share with our audience, or advice you'd like to share, or can they find you?
Yeah, I hope that gave some idea of space architecture as a discipline, and also that if you are interested in space, or you want to do something for space, it's much more than just sci-fi cool images. It's actually, even though it may seem that it's too much of engineering, or it's a lot of engineering, but that's what makes it really interesting to deal with. And that's there is a big field for architects and designers, and anyone who are interested in making life better everywhere, not only in space but on Earth.
Okay, great. I'll put the descriptions for the master's program also in the YouTube description.
Yeah, thank you.
Okay. Olga, it's been an honor to have you here. Thank you so much for sharing your insights and expertise.
Thank you. It was very cool to talk about it a little bit.
Likewise. To everyone listening, this is the Omar Alayli Podcast. Thanks for joining us, and keep exploring.